Hey, good morning, everyone. Can you hear me? Can you just give me feedback? Perfect. Thanks, Bernd. Cool. Okay, please mute your microphones. If you have questions, post them in the chat, and I'm going to answer the questions afterwards, okay? So and as you know, or maybe you already know, that we're going to record the session. So without having any disturbance through the participants' audio, we have a clean recording, and then we're going to publish the recordings on YouTube channel. Good morning. And also the slides you will find on our homepage. Yeah, the link will be in the video description. Also later on you will find it on our homepage. Okay, so with that being said, welcome everyone to our DYNAmore Express webinar. And today we're going to talk about the arbitrary Lagrangean-Eulerian method, or for short ALE. And I think there are many misconceptions regarding this method, because when you take a look on the method and you see like simulations running this method, you sometimes see, wait, let me just, please mute your microphones. Okay. Okay, so like I said, we're talking about the arbitrary Lagrangean-Eulerian method. And when you see this method, you see that quite often you see them in the terms of something like fluid mechanics, but also you see it in terms of solid mechanics. And in this webinar, I'm going to introduce you to the method, how it's used in LS-DYNA, also give you an overview, and also try to somehow elaborate the basic concepts. Yeah? And also give you a couple of application scenarios where you can apply it, what kind of features does the implementation in LS-DYNA support, together with the ALE method. Okay, so let's start with the introduction. So first things first. And so first of all, let's give you a little overview on LS-DYNA. I mean, many people know LS-DYNA as this solver for explicit dynamics. So everything with this short-term, rapid processes, these are simulated usually with LS-DYNA, because LS-DYNA was originally designed for having like simulating quick events like impacts, explosions, and so on. But nowadays, the code has developed quite further, and now we consider LS-DYNA more as a multiphysics solver. And this is basically pretty briefly explained on this chart here. So basically, we were starting with a mechanical solver, which was supposed to be explicit, so for short-term dynamics. But over the years, LS-DYNA has progressed quite a lot. And we get, back then, we got a couple of new modules. For instance, we got a thermal solver. We have now a solver for particle methods. We have a solver for fluid mechanics. And we also have a solver for EM, electromagnetics. And all these different modules, so to say, are somehow combined into one solver. So that means when you get a license from LS-DYNA, you don't have to buy additional packages, at least not so far. Yeah. So if you get a license from LS-DYNA, you get basically the whole package. And you're free to choose what kind of solver you want to use. You want to do something mechanical, you go with that one. You want to do fluid mechanics, you can go with that one. But the important part to note here is that you can combine all these different solvers with each other. Yes, for instance, we do some mechanical solver to compute structural deformation, and then this structural deformation is then fed into the fluid solver to recompute something here. Then you get a pressure here that's again applied on the structure, and then you have this interaction. Yeah. You can also have a thermal solver, particle methods, and so on and so on. Yeah. So I just want to point out that LS-DYNA nowadays is more than just this explicit solver which it used to be. Yeah. So, and what we're talking about today is part of the mechanical solver. Yeah, the ALE method is actually part of the mechanical solver. Although you can apply ALE method also for fluid mechanics. Yeah, but I'll get back to this in a minute. Okay, so here's an overview of what we're going to talk about today. So first of all, of course, I'm going to introduce you to the fundamentals of the ALE method, how it's implemented in LS-DYNA. We talk about Lagrangian structure interaction. We talk about moving reference frames. We talk about a little bit of output, and also talk about a structured ALE, which is basically an improved implementation of the ALE method, which you're supposed to give you better performance and makes the whole treatment of ALE in LS-DYNA a little bit more user-friendly. Okay, so let's talk about the fundamentals. So what is the ALE method? And basically what the ALE method was trying to solve is how to deal in a finite element simulation or a finite element based simulation with heavy mesh distortions. Yeah, so this is basically a problem. This is a beam, yeah, which is crashing into a wall. And usually what you observe here is you get highly deformed elements down here. And as you may know, the finite element method is not suitable for heavy mesh distortions. Yeah, so if you have degenerated elements, the finite element method usually fails. Yeah, and this is the problem we have to deal with. So large deformations and an element performance degradation. Oh, okay, there's a misspelling here. Anyway, so what's the solution to the one? One solution might be, okay, then if we have highly distorted meshes or elements, we can just do a remeshing step. Yeah, so then we recreate a mesh, trying to generate elements which are following the deformed structure, but having like less degenerated elements, considering each element. Yeah, or the other approach is the so-called ELE method. Yeah, and this is what we obtain from the same example using the LE method. And what you notice, or if you compare this, the bottom of this beam here, yeah, you see highly deformed elements here, and you don't observe it here. Yeah. And this is basically actually what the LE method is doing. Yeah. But how it works, I get to this in a minute. So here again, you see it more in details. Yeah. So this is a usual Lagrangian deformation. Also here's a misspelling. And yeah, you see these degenerated elements here. So there's really flat hexa elements. And here in this ALE approach, you see that the elements looks more regular deformed. Yeah. And so basically this is the benefit of the ALE method. Yeah, so you end up with having less deformed elements. Okay, before I get into the particulars of the method, just a little bit brief overview about what we're actually doing in numerical simulations. And basically what we always do, and I think this is important to keep in mind, in simulations, we're trying to solve partial differential equations. So we have like partial differential equations like the mass balance, momentum balance, energy balance, and we're trying to solve these equations. Yeah? And part of the solution process, is, first of all, decompose your partial differential equation into spatial distributions. So you're going to discretize the PDE in space. Yeah? And this can be done by finite element method, smooth particle hydrodynamics, EFG, and whatever. Yeah, this is the first step. So you're trying to resolve the spatial dependencies. And most commonly, people use finite element method, and this is what we also use in the LE method. Second step is then the time discretization. So we decompose our whole process in time, and this can be done by backward Euler, central difference schemes, whatever. There are many schemes out there, and these two discretization steps, so first space discretization and time discretization, make up or rearrange your equation in such a way that you can solve it by a computer, so by using numerical solution procedure. Okay, and what is now the LE method doing? Yeah? Usually we can classify method being either a space discretization or a time discretization method. In this one here, it's neither one of these. So the LE method actually uses finite element analysis. That means I introduce a mesh, I have nodes, I have shape functions between the nodes, and then I'm using a time integration scheme, for instance, the central difference scheme, to order to obtain a system of equation which I can solve with the computer. However, and here's the twist of the LE method, the update, how to proceed in time from one time step to another one, yeah, is slightly different in comparison to a regular time discretization scheme. Yeah? So what we're actually doing in the LE method, we're using a Lagrangian description for the deformation, and then we use an Eulerian formulation to correct the distorted meshes. Yeah? So we have to deal with Lagrangian and Eulerian formulations in this method. Yeah? So this is actually the twist of the LE method. Yeah? And also, as the name already implies, LE means arbitrary Lagrangian Eulerian. Yeah? That also says. Yeah, so it already contains the names Lagrangian for the Lagrangian description of the time advancement and the Eulerian description. Yeah, so we have both of these in the method. And what you can do with this, yeah, basically you, like I said before, you can see LE method applied to heavy solid deformations. For instance, this one, yeah, that could be a solid, maybe a steel, which is heating up, and so it's pretty soft, and then you do some kind of bulk forming. Could also be a paste, whatever. But you also see ALE applied to solid mechanics. Yeah, so this is like a drink thing container, and you can see that the sloshing of the liquid inside of the bag. So that now we have applied ALE method, but to something which is more like a liquid. Yeah, so we can, and this is actually often confusing to people. Yeah, that ALE method, the way it's designed, can be used to simulate solid mechanics problems, but also fluid mechanics problems. Yeah, of course, it's not actually a fluid solver, but to some extent you can compute fluid mechanical problems as well. Okay, so let's get back to the method. Like I said before, ALE comprises two approaches, which is the Lagrangian and Eulerian formulation. And to understand the method, we need to somehow recap what you probably remember from your studies at university. There are two ways of describing the movement of a body or of some kind of structure. Yeah, the first one is the so-called Lagrangian description. Is that one here? And this is often referred as the material description, because what we're doing, we are locating a special material point on my structure, and as the structure deforms, I'm following this point. So there's like an observer sitting on this point, and as the structure moves, like translates, rotates, stretches, compresses, whatever, I'm observing what this point is or what's happening to this particular point. So I'm actually following this point. So I'm fixed on the material. Yeah, and this is usually also what you do in the finite element method, right? So you have the node, or you have the element, and then as the structure moves, you're following this element, and so you're observing what kind of changes this element is exposed to. Where does the element translate? How is it stretched? How it's compressed? Yeah, so this is the Lagrangian description. Yeah. On the other hand, there's also, from a theoretical point of view, the so-called Eulerian description. Yeah? And the Eulerian description is a spatial description. And what we do instead, so in comparison to Lagrangian, is we have an observer, and this observer is looking at a fixed point in space. So it's looking here, and then as the material moves, so this one, he's seeing a flow of material to this spatial point. Yeah? And this is description which is often used in fluid mechanics. Yeah? And in fluid mechanics, you have your cells, and then you try to compute what's the velocity of the material passing through this element in all the different directions, and so on. So this is basically often used for fluid mechanics, and this is used for solid mechanics. Yeah, and in ALE we combine both of them. Yeah, we bring both together, and how this works we see on the next slide. Okay, so here's a short recap. Lagrangian description: you have your mesh. You apply a load to the mesh. Maybe you pull on this end here, and what you get at the end, this is your deformed structure on the right hand side. Yeah, in this case you get some kind of distorted geometry, and you see this element here was moving sideways and also got somehow distorted a little bit. If I do this in a Eulerian description, I predefine a mesh. Yeah, I apply the same load, and now I see that the mesh is fixed, but now the material moves through the mesh. Just the Eulerian description. And ALE is combining both. Yeah, so first of all, we have some kind of Eulerian mesh here, and now we apply again the same load. And now the material, first of all, we can move the mesh in some way. So what we can do is, for instance, we can say, oh well, let's move the mesh, this Eulerian mesh, let's move it together with some kind of average movement velocity of the structure. Yeah? So I can move the mesh, and at the same time, the material moves inside of the mesh. Yeah? And actually, this is actually what the ALE method is doing. So arbitrary, Lagrangian, Eulerian. Yeah? So using both methods. First of all, we have the movement of the mesh, yeah, which is from the Lagrangian, and then we have the flow of the material inside of this moved mesh. Yeah? And this is the Eulerian part. Yeah? So this is basically the concept. So, and I think this is important to understand that in ALE you're combining both methods. The question is now, how is this both brought together in the advancement from one time step to another one? And I think this is, I'm trying to illustrate here. So pretty briefly, I mean, we also do have a class which is solely focused on the ALE method, gives you more background, but for that webinar, I think it's okay just to outline the basic steps. So first what we have, this is our Eulerian mesh. Yeah. Inside of this mesh, we have some Lagrangian structure. Yeah. Now, based on the loads, we're going to distort the geometry. So for instance, we're going to move this body here inside of this mesh, and what we get in the first step, which is a regular Lagrangian step, as we would get from like regular finite element analysis is we get a movement of the mesh, we get a movement of the structure, and because as the structure moves and the nodes are tied to the structure, we do get a distorted mesh, as you can see here. Right, this is the first step. So first we do just a regular Lagrangian step as it's done in the finite element method. The second step is, and this is the so-called ALE, intermediate ALE steps, is first of all we do a mesh smoothing, which means we're going to correct the mesh distortion here. So we pull back the nodes to either to the initial position or to some kind of extend to have some kind of smoothing strategy. This is the first step, the mesh smoothing. Just correct the distorted mesh, and then we have the so-called advection, and the advection deals with the so-called material flow. So if you compare this one here, so here I have the distorted mesh, and now think of, okay, I'm trying to correct these nodes here. That means I'm going to change the mesh, but this actually means if I look on the structure that material has to flow from one element to the other in such a way that the Lagrangian structure maintains its original shape. And this is the so-called advection step. And this is the Eulerian step, so to say, because now you have a fixed mesh, and your material flows through the mesh. Again, this is a combination. First Lagrangian, you get a mesh distortion, then you have this mesh smoothing, which is trying to undo the heavy mesh distortion, and then in order to correct this mesh smoothing, you need to do an advection step. And basically this is how the ALE method works. Just keep in mind all the time. First of all, you have a Lagrangian step, you get a mesh distortion, then you have your LE intermediate step, which includes first a mesh smoothing. There are different methods to do this, and then you have your advection step. That's it. So this is the method. As a side remark, of course, we are still working here explicit. We still have a CFL condition. That means we have the time step is limited by the flow velocity in the structure. This is just an outline. But I think to understand the method, this one here is more than enough. Okay? Okay, so that's the ALE method. That's it. As simple as that, right? And I think it's important to understand this step because every time you run into issues or you want to think about how do I apply some boundary conditions, think about that way. First of all, you get a mesh distortion, and then you have the correction of the distorted mesh. Just think of this all the time. Okay, so what can I do with this one? So first of all, the obvious one is I can define a structure or a mesh. It's a Eulerian mesh, and inside of this mesh, my structure is moving around. And we often refer this to a so-called single material ALE. That means we have a material which is defined by some material law, elastic, could be fluid mechanics, whatever. And the rest of the material is treated as a void, so as a purely empty material. That's one way of doing this one. This is all single material ALE. What I also can do is I can somehow fill my Eulerian domain not only with one material, but also with different materials at the same time. So that each material follows its own material law. For instance, this could be, I don't know, some elastic material, this could be some gas, this one could be a liquid, and they're all somehow working together. And this is something where the ALE method works more like a fluid mechanics method. When you do this multi-material ALE. Okay. So the question quite often is, when do I have to do what? And so when is it okay to go single material? That means I have one material I define by some constitutive law, elastic, rubber-like, a fluid. And when I have to do multi-material LE? And basically the answer is, whenever you think that the interaction between these different materials is important for your whole process, then you have to do multi-material LE because then they can interact here. If you think the surrounding of my structure I want to analyze, so this one here, is not important, then you go with single material. So for instance, if you do a forming simulation, you model your bulk material which you want to deform as a material following some material laws, and the rest of the inside of your Eulerian domain you model as void. So it's not treated as a liquid or as a fluid, doesn't have viscosity, doesn't have a density, and so on. That's that way. But if you think there's some interaction between the fluids or between the materials inside of the structure, which is of significance, then you have to go with the multi-material approach. Yeah, so just as a guideline, when to use what of these. Okay, so this was a brief quick overview or introduction into the LE method, what's under the hood, so what's working in the background. And now we move on to how this method is defined in LS-DYNA, or how can I use it. And here I want to give you a quick overview of some important keywords. Some of them I'm going to address here, some of them I'm going to skip. If you want to know, like I said, I mean, there's a class solely focusing on the LE method, but I think this webinar, or the goal of this webinar is that we're trying to answer commonly asked questions in this webinar. So maybe once you work with LE, maybe you can go back to the video, just think, okay, how did he do this? What kind of keywords I can use? And yeah, so here there's keywords which are important. The first one is called as a controls keyword, yeah, to somehow change some general settings of the LE method. For instance, what kind of method I'm going to use for the advection step, how I'm dealing with reference pressures which are outside of the LE domain. I can also deal if I have multi-material LE, yeah, there's a set of keywords dealing with multi-material, which are always ALE_multi-material for the multi-material definitions. You can set the initial multi-material distribution, so in which part of my domain is what material. I have a couple of material laws, most of them are based on the regular mud material, but there are also special ALE materials, which are most often fluid-like materials, and quite often I also need to have an equation of state. I can do fluid structure interaction, or to be more precise, Lagrangian and ALE interaction. For boundary conditions, I can use most of the time the regular boundary keywords, which I have from the finite-element method. And also there are a couple of keywords related to the post-processing, to the output of data, but I get back this later. Okay, so first of all, when I do LE, if I want to do LE simulation, how do I do it? Yeah. Actually, it's quite simple. So if you have a structure and you have your simulation, which is run by let's say a finite element analysis, like the beam we had at the very beginning. Yeah, if you remember that one. So what you do is usually you start with you do a finite element or hexaeder analysis. All you have to change is you have to change the element formulation from 2, which was the if it's a hexaeder element, it's a linear underintegrated hexa element. Yeah, oh no, it's a fully integrated one, sorry. And what you have to do is you simply change the element formulation. And if you go to the manual, you find a couple of element formulations which are related to ALE material method, or here also Eulerian goes in the same direction. Yeah. So all you have to do is, if you have a finite element analysis, you change, for instance, your element formulation from number 1 or number 2 to number 5. Yeah. And what you do in this step is that you incorporating this new update from one time step to another one. Yeah, so remember, if you do finite element analysis, you apply a load, you have a deformed mesh, you apply a load to your nodes, then you have a mesh distortion, and that's it. If you now change the element formulation to this number 5, for instance, you additionally incorporate this mesh smoothing strategy together with the advection. That means in a regular finite element analysis, you have applied a load onto your mesh, you get a mesh distortion, done. Yeah, in each time step. If you do the LE method, you get, again, first Lagrangian step, which means mesh distortion, but then with element formulation number 5, you additionally include mesh smoothing, yeah, and the advection step in order to correct the given mesh. Yeah. And also, if you have multi-material, then you can go with 11. If you have multi-material, or if you have multi-material, you go with number 11. If you have the special case of a multi-material with the surroundings being a void, yeah, it's like an empty space. So like in this case here, yeah, so let's say this one is not in air, but something, just a vacuum or whatever. Then you go with number 12. If you want to have a real multi-material, or formulation with all the fluids or all the materials interacting in some way, then you have to go with 11. Yeah. So quite often comes the question, so what's the difference between the ALE and the Eulerian? And this is actually seen on this video here. And basically you see that in the Eulerian part, you have the fixed mesh. So the mesh is just predefined. You have your structure inside of your mesh. And if you do this one, the mesh is fixed and your structure flows inside of the mesh. Yeah. And this may look from the outside like a fluid problem. Yeah, you have a fixed mesh and then your material moves inside of the mesh. But actually, just keep in mind, we're still in this ALE approach. Yeah, that means, even though in this case, from your perspective, it looks like that the mesh never deformed. But again, remember what we're doing in the inside. In the inside, we're doing, first of all, we're doing a mesh distortion, and then we do a mesh smoothing, and then we do a advection step. Yeah. And this is done in each time step. So that means from the outside, it looks like the mesh is fixed, but in the computation procedure, it's not. It's like a distorted mesh, correcting of the mesh, and then the material flowing through the mesh. Yeah. So just think about this all the time. I think this is really important. And this is what most people get wrong when they think about the ALE method. Yeah, just think about these 3 steps all the time. Yeah. So this is the Eulerian one, and this is the ALE part. And like I said before, ALE means also the Eulerian, the mesh can deform. Yeah. So you have 2 parts, structure inside of the mesh, but still the mesh itself can also deform. And this is the arbitrary part in the arbitrary Lagrangean-Eulerian method. Okay. So how do I do it if I want to do multi-material definitions? And I think I already mentioned it. Yeah, well, you have to switch the element formulation to number 11. That's it. Yeah. Okay. This is the first part. The second part is, of course, you have to define your multi-material groups. And I don't want to go into the details here, but usually what you do is you're using this keyword ALE multi-material group. And here what you can do is you can think, if you have a structure or if you have some problem with multiple materials inside of your domain, you can think of that you're trying to group them together. So same material goes in the same group, and so on and so on. And then you can create different material groups. And these material groups are supposed to kept separate during the simulation, but can interact with each other. Yeah, that means each material group, maybe this one here, is a group of materials composed of steel. This one here may be air, this may be a liquid, and this might be something else. And these are then inside of your Eulerian domain interacting with each other. Yeah, and I think it's important to note, because quite often we get a question, what kind of materials do I put into one group, and what do I keep separated? And as a general rule of thumb, the question you have to answer by the process you want to model. So just think of it that way. All the materials in the same group can mix. So during a simulation, let's say you have one part of your material group number 1 here on the right-hand side of the simulation of your domain, and then another one on the right or the left-hand side. And now the process, whatever you're simulating, is making them flow together, right? And if they are part of the same multi-material group, they somehow can mix and become one part. Yeah. If they, however, are assigned as different material groups, they cannot mix each other. So you always have an interface between these 2 material groups. Yeah. So think of it that way. Do I want these 2 materials to be mixed with the other, so it means become one during the simulation? Then I have to assign them to the same material group. If I don't want to mix them, I keep separate material groups. Yeah. That means maybe you have 2 different gases. Yeah. Then one gas is material group number 1, and one gas is material group number 2. And then if they're 2 material groups, they're not mixing each other, they always kept separate, and you have an interface between these 2 gases. However, if they I have 2 gases, but they're going to mix in some sense, yeah, then you're going to assign them to the same multi-material group by using here part sets instead of parts. Yeah, so with this one here, you can choose if it's a part or a part set. If you want to mix them and assign them to the same multi-material group, then you make a part set out of this one. Yeah. And I think there's something tricky about this keyword. The thing is, you're using the part IDs here or part set IDs here. However, it's right. I think at least to my knowledge so far is that the first line is automatically ILE material group number 1, second line is number 2, 3, and 4. And I think there's no way so far to give it a user-defined number. Yeah, so I think this is a little bit tedious in my point of view. Sometimes it makes it a little confusing, but that's the way it is. Okay, so this is the basic concept. Next one is we want to talk about, which is quite common, I want to make it interact with some Lagrangian structure. Yeah, that means I have a regular finite element analysis with like meshes, with like solid elements, shells, whatever. And these are usually sometimes embedded into some Eulerian domain and want to make them interact. Yeah, for instance, here, this is a quite common example. So this is a ditching simulation of an aircraft structure. Yeah. So the aircraft structure itself is modeled by shells in a regular finite element manner, yeah, as usual, as you would do it. And the liquid here is modeled as the Eulerian ALE method. Yeah. And I want this quite commonly, I want to have an interaction between both of them. Yeah. And the thing is, why do I want to somehow separate it? I could also somehow define the structure as part of the ALE domain. Yeah. But the ALE method is way more computation expensive, so that's why I usually try to model what I can model as a regular finite element approach, because finite element method is very efficient, it's very fast. However, it lacks the strong deformations. So I'm trying to group what parts of my simulation undergo high deformations that should go into the ALE simulation, and which parts have moderate distortions, then these go as a regular finite element approach. Yeah, by that I can somehow combine the efficiency of the finite element method and then and also use the complexity or the possibility of the ALE method to handle severe solid deformations. Yeah. Okay. Yeah. So as a guideline, FEA, so regular FEA, so to say, for solid structures which have a mild deformation, and ALE for heavily distorting materials. Usually this goes to pastes, liquids, and so on, gases. Yeah. Okay, so how do I couple these together? I don't want to go into details here, but actually, basically, the coupling approach is the same as in the finite element method. And what you can do here is you can use a constraint-based method with respect to the ALE method. It means this is my ALE element here. This is my Lagrangian structure. So this is the shell structure inside of my ALE domain. And what I basically do is I take the velocities in this constraint method of the ALE structures. I'm going to interpolate using the shape functions of the finite element method, which is still behind the ALE method, yeah, onto this coupling point here. And then I'm going to prescribe the velocity being the interpolation of the nodal velocities of this element here onto this location. Yeah, so I'm going to prescribe the displacement of the structure using the nodal velocities of the ALE material flow, so to say. This is one way of doing it. The other way is I'm using a penalty-based method, and this is quite commonly when we talk about contact mechanics and LS-DYNA. And the idea is actually quite similar. Also here we're going to use so to say the pressures or the movement of the material inside of the Eulerian domain. But what we, instead of prescribing this velocity of the Lagrangian structure, also here the Lagrangian structure is the slave, we're not trying to interpolate velocities onto this coupling point here, but instead we're going to prescribe a force which is going to be considered as some kind of penalty force, and we're going to penalize every time the constraint of, let's say, non-penetration of some kind of material is violated. Yeah, so that means we assume that there's also constraint in, yeah, also like here, there's a constraint in here, and the constraint is, let's say, the Lagrangian structure has to move with the material of the ALE. Yeah, and every time this violation is violated, or this constraint is violated, we apply the penalty force to somehow correct for it. Yeah, and the penalty force usually is just a simple spring is some kind of linear relationship between penetration or violation amount proportional to the penalty force. So it usually applies to some kind of spring load. Yeah, you can think of the penalty method as a spring which becomes activated once the violation is active. Yeah, and the higher the violation, the higher the spring force in order to correct it. And if the violation vanishes, then you're good again. Yeah, and the thing is, it's exactly working like in the contact mechanics in LS-DYNA. Yeah, so there's nothing fancy about this one. Yeah. As a remark, in order to activate this interaction, there's this keyword constraint Lagrangian solid. There are many parameters in this one, but only a few are necessary. And one of the most important ones is the C type, which is the contact type. And quite often we're not going to use the constraint-based method, because the penalty method is more accurate in most of the time. Yeah, so C type equals 4 activates the penalty-based method. Yeah, and this is mostly recommended for many cases. Okay, so here's an overview about the constraint Lagrangian card map. So again, similar to the regular contact definitions in LS-DYNA, we choose what is the master type, the slave type, what's the master type, and then you have the IDs. Just keep in mind, in LE formulation, the Lagrangian structure is always the slave. Yeah. So here goes your finite element, your regular finite element approach. Yeah, as a slave. Yeah. And the master is the mesh of the Eulerian material. Yeah. I don't want to go all the details, but what I want to point out is you have a couple of control parameters. Also here you have a penalty factor for the contact stiffness if you have the penalty method. And here with the M cube, you can control with which materials or multi-materials inside of your ALE domain the structure is interacting. Yeah, you can interact with all of them. You can interact with, I don't know, the one with the highest density and so on. You have different choices, but I suggest to look on this in the manual regarding this keyword, because here you can define with what is the structure interacting. Yeah. And what is important to note is this I leakage, this N quad here, and this is something we need to use in order to control leakage. Yeah. So first of all, what is leakage? And basically it means that the contact strategy we are choosing here is not working properly. So on the left-hand side, we have this one here. Yeah, and you can see that here, this is our liquid-like structure, this is our Lagrangian structure, and you can see that somehow, yeah, the contact is not working properly in this area here in the middle. Yeah, so we have a leakage of the, I don't know, ALE material, so to say. Yeah, and the reason for that is quite simple. The problem is that, just think about again how this method works. We're going to apply this penalty load, yeah, on the Lagrangian structure, but we only apply it on these coupling points. And usually the coupling points are the nodes of the FE mesh. Yeah? And the problem is, for instance, in this particular case, you can see it, we have a node here, we have a node here, then we have here, you have your shell element here, and you can see that the shell element now passes a whole ALE element. But in this element, you do not have any coupling points. So there is no way you can apply a penalty force in here. That means this liquid in here is not somehow constrained by a penalty force, so you can just move here and pass through. And this is actually what's happening here in this one. Yeah, because there is no coupling point inside of this ALE element. And what you can do is, of course, you can refine the mesh of your LE structure. And that way that you have a couple of coupling points in your inside of each LE element. Yeah, so for this, you could do a mesh an element here, 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 here. But if you do explicit, then you have smaller mesh sizes, then you have smaller time steps and so on. So I think maybe this is not that straightforward. But what you can do instead is you can reduce more coupling points. Yeah? Instead of having a finer mesh, you just keep this mesh, you can introduce more coupling points. And this is done by this N quad parameter. Yeah? For instance, you can choose like N quad equals 4 means you have 4 coupling points in on your LE structure. You have your nodes here, and then you introduce 4 more coupling points. And N quad, of course, is in spatial directions. So you have, if you put N quad equals 4, then you have in one spatial direction on the surface, you have 4, and then another 4 in the other direction. So in total, you now, with n quad 4, you have 16 coupling points on a 2D structure. Yeah. So of course, that makes computation more expensive. I mean, you can check it if you have a small example. Try to increase the number of coupling points, and you see we have a drop in performance quite significantly. But I mean, this is correcting your leakage. Yeah. So basically, you have two ways. Either you refine your Lagrangian mesh, which is often devastating for performance because also then the time step goes down, or you just increase the number of coupling points. And that's why we have this parameter, because it's still more efficient than refining the Lagrangian structure. Yeah. And as a rule of thumb, it's also written here, we suggest to have approximately 3 coupling points inside an LE element, just approximately. Yeah. Either your mesh size is defined in that way, that you have 3 nodes of your Lagrangian structure, or you have 3 coupling points in it. Okay, next up, what might be important is the so-called moving reference frames. Yeah, if you remember before, so far we always had the Eulerian mesh, which is defining the LE domain, so to say, and inside of this domain, the material can just move around as it is. Yeah? But now let's say, assume you have some kind of problem where you have a structure which is doing a lot of translation inside of this LE domain. Yeah? That means you have to create a huge LE domain, yeah? And then you have a lot of elements where there's no computation necessary because nothing is happening there. Yeah? So it's, again, devastating for your performance. But there's this moving reference strategy, which means we can move the Eulerian mesh in order to somehow encapsulate our material of interest inside of the Eulerian domain. And the keyword we are referring to here is the so-called ALE reference system group. And also here, there's a whole more to this one than I'm showing you here right now. Because you can think of there are different ways of how do I define the movement of the Eulerian mesh. Yeah, for instance, so there's an example down here. Yeah, so let's say this is something similar to a bird strike. So this is your Lagrangian structure. This is my Eulerian ALE domain here, so the yellow one. And inside of this one, I have my, so to say, material of interest. Yeah? Oh, sorry, that's not, I want to show this one here. Yeah, material of interest, then we have the impact, and this is what we have. But you'll see that the structure is moving together. So with that, I'm saving computation time. Yeah, if I wouldn't have done this way, I was supposed to have a large ALE mesh somehow covering this space in order to have a mesh in which the ALE material can move inside. Yeah? So with this one, I'm just saving computation time. And as you can see, the question is now, how do I define this movement? And there are different ways. So this is chosen by the PR type here. There are ways of where you can choose a coordinate system which is moving. You can, I don't know, define the movement of this one here by using the average movement velocity of the material inside of this Eulerian domain. I mean, just take a look on the key on the manual. There are different ways on how to define it. You can even constrain some of the movements. Yeah, you can say no. I don't know. I want to have all the translation the constraints free, so the mesh is not constrained in any way. It can just follow the structure as it is. I can somehow make it, I don't know, expand and shrink. And this is actually the second one here, which I was supposed to show you now. Yeah, this is the same one. But in this one, we are not limiting the expansion and contraction. So we just say the expansion and contraction is somehow following the average velocities inside of the structure. Yeah, and that is what you get then. Yeah, you can do something like this. Yeah, so if this one goes a little bit to the side, if you just compare to this one here, because we have the spreading of the material sideways, and now we are pretty close to the domain. Yeah, and we are close to just ALE material leaving the structure, or leaving the ALE domain. Yeah, this is not what we want. We want to keep it inside. And then for that, we can somehow use this. We can release some of the constraints of the ALE mesh. Yeah. But like I said, I don't want to go into details here. I just want to give you an overview and take a look on the manual. And like I said, there are many different ways on how to define it. I mean, you can also define enclose, make sure that the ALE, this mesh here is always enclosing, as trying to estimate the size of this material inside of the LE domain, and then you're trying to rearrange the mesh so that you have is also some kind of buffer to the boundaries and so on. I mean, that, like I said, I mean, there are many different ways how to do it. Okay, next up, and this is something really important because we get a lot of questions about this one, it's the output. Yeah. So, and the most important one we get all the time is, once I've done an ALE simulation, especially multi-material simulation, how do I see my different materials? Yeah, because if you open this one in that way, as you do usually, you just don't see it, right? You just see the initial ALE mesh, the initial distribution, you run your simulation, but nothing moves inside. So you don't see the movement of your ALE material. And the reason for that is that what you're showing LS pre-post is you only see the initial mesh. So in order to see your movement of your fluid, what you do have to do is you have to go to this in the LS pre-post, you have to go to the model part, then you go to select parts. I think it's also you can also use F2 to access this pop-up window. And then you have to tick this checkbox here, which is called Fluid ALE. And then in this one, you now can choose the ALE groups you have defined. Yeah. And then you choose the group you want to visualize. And then if you then visualize your simulation, you see what you're actually seeing. Yeah. By default, you just see, and for this particular case, you just see this one here. This is the Lagrangian structure. Is the car shape here in this one. And number 200 is the whole ALE mesh, but what you actually want to see is this ALE group number 2, which is the liquid inside of this car-like structure. Yeah. So for this particular example, if you just open it as pre-post, you just see the first two. Yeah, but this is not what you want to see. In order to see what you actually want to see, yeah, check or tick the checkbox Fluid ALE, and then you can choose the ALE groups, and then you can visualize it. Yeah, and this is a pretty common question we get from users which are new to ALE method. Yeah. Okay, and then a couple of other databases. Again, I wanted to go into details, and but the database ALE keywords to somehow modify the output order of history variables. If you have fluid structure interaction, you probably want to know what's the pressure close to the surface. Then you can define so-called pressure sensor, so-called sensors. Yeah, these can also define with an offset to Lagrangian structure. And then you get, for instance, pressure. You can measure the pressure. You can measure whatever velocities inside of your ALE domain but using it relative to your moving Lagrangian structure. Yeah, this is pretty helpful for measuring pressures, for instance. Yeah, and what I also want to point out is, if you have history variables in your ALE material, let's say a temperature, I don't know, there are some materials which are somehow dealing with burning of material. Then you want to know what is the fraction of my unburned and burnt material. And these you find in the history variables, but in order to activate it, you have to use the keyword database extend binary. And here is the parameter NEIPH. Yeah. And there you have to set a certain value, 10 or whatever, in order to activate an extended output of history variables. Yeah, this is also a common question we get. I have this material, it's supposed to have this history variable, but I don't see it. Yeah, and the thing is, you have to do is, yeah, that's the solution to this one, activate it. Okay, last one, and this is basically is a whole new chapter, but I keep it short. And this is, I'm talking about a so-called structured ALE. And the structured ALE is basically it's a new implementation of the ALE, but it's trying to optimize the computation. Yeah. So the whole theory is the same. The steps are the same. Yeah. So we have the same old ALE theory. We have the mesh smoothing. We have the advection. Lagrangian structure works exactly the same way. However, it's just a different implementation. And what we're doing here, we're assuming that the ALE mesh does have a predefined shape, so to say. Yeah. If I go a little bit back, yeah. So here, for instance, also here we have like a regular, I don't know, geometric simple shape, and this one is just a block. But the ALE mesh could be anything. Yeah. There's no limits to this one. In the structured ALE, however, we are starting with a structured mesh, and that means we can somehow optimize the algorithm because we know the mesh we are supposed to have is structured. And you may say, okay, then I'm less flexible on the problems I want to solve. Yes, but you also gain a lot of performance. Yeah. So if your problem you want to solve is suitable, you should go with a structured LE, yeah, because it's way more performant. If not, then of course, then you have to stick to the old one. Just to give you an idea, I mean, this is a tank. I mean, here, so this is the Lagrangian structure from the outside. Inside, you see here some kind of liquid, and we're going to shake this box, and also there's an impact from another material. Yeah, so this is what we're computing, and then we have another one here and interacting, and then we have some flow here. I don't know what kind of material this is, but anyway, what I was interested in is to compute performance. And with the LE method, you're running the simulation in approximately 90 minutes. With the SLE method, you have just 1 hour. Yeah, so there is a performance enhancement. Sometimes it's even better. Sometimes you don't have any performance enhancement. I don't know exactly what's the reason for that, because I didn't do the implementation. I don't know the particulars. But in many cases, you do have a better performance using the structured LE. Yeah, so if the problem you want to simulate or compute allows for structured LE, go with the structured LE. Yeah. Also, mesh generation is way easier. So basically, what you do in the structured LE method is you define so-called mesh seed in the coordinate directions. So let's say, I don't know, 100 nodes in X, 20 nodes in Y, and I don't know, 10 in Z. And then the structured LE will generate this mesh on the startup at the simulation. Yeah. And this is often quite easier because you also can somehow easily redefine your mesh. You can work with refinement in areas, and it's way easier to handle. Yeah, apart from the performance part of this. But in general, keep in mind the theory is the same. It's just supposed to be to make things user-friendly. And what I also suggest is, if you use the structured LE, use one of the latest versions of LS-DYNA you can get, because there's a lot of implementation and going on with the structured LE. Yeah, so just keep this in mind. Okay, so here for a few keywords, and basically, I want to go into details because due to lack of time, but all the structured LE keywords start with LE_structured. Yeah, and with that, you get a whole new class regarding to this keyword. And also feel free to check out www.dynaexamples.com, and there you find a couple of examples which you can use for starting your new LE or LE structured. And so for instance, if you want to create a mesh, there's this keyword controlled LE structured mesh control points. Yeah, with that you can define a mesh seed along the coordinate axis, which could be the global coordinate system or some local coordinate system. Yeah, you create a mesh seed, and then you apply the LE structured mesh to actually create a mesh. Then you have it. Then you just, in the second step, you have to distribute the material inside of your mesh. Yeah, and then for that, you first have to create this LE multi-material groups. And then you can use the keyword initial volume fraction geometry in order to populate your LE structured mesh with material. Yeah. So these are the important keywords you have to use. Yeah. So LE structured mesh control points to define the mesh seed on the edges, then LE structured mesh to create the actual mesh. Then you have to define multi-material groups. Yeah. So part this is this group, and then you use the keyword initial volume fraction geometry to populate your mesh. If you want to, I mean, you do have a little bit of possibilities to somehow modify your structured mesh. I mean, you start always with a block, yeah, because you're always aligning according to the coordinate system. But what you can do is there's a keyword which is called LE structured mesh trim, which allows you to somehow just trim away some parts of your structured mesh, which is not needed. For instance, you start with a block, but then you decide, okay, I want to cut out a few sections because no material is going to be there. Then you use this trim keyword. So that means you're still using this more efficient LE structured implementation, but you'll be able to create more complex meshes, so to say. Yeah, and I think what is also important to note, if you already have a simulation running and you want to see, and this seems to be suitable for the structured LE, yeah, you can use your input deck with the regular LE method, and in the LE structured keyword, you can set the parameters control point index, which is a CPIDX, which is control point index, set this to -1, then LS-DYNA will at the very beginning take your existing ALE mesh, convert it to a structured ALE mesh, and then continue with the structured ALE. Yeah. You also get an output file. I think it's something structured ALE include something, and there you find the keywords, which is the ALE structured keywords, and these keywords which are defining your new generated ALE structured mesh. So it helps you with the conversion from the old ALE method to the new one. Yeah. So this is pretty convenient if you want to give it a try. Okay. With that, I'm at the end of this introduction to ALE method. I mean, this is not a whole introduction. It was just a quick overview to give you an idea, okay, how it works first of all, to answer some commonly misconceptions we get in the support, but also give you an overview what you can do with it, what kind of keywords. Remember the moving reference frames, the structured ALE, the Lagrangian contact. Yeah, and yeah, let me just wrap things up. So, like I said, I think it's really important to understand that ALE method, what it actually does in the background. So just keep in mind, the first step we're doing is we perform a Lagrangian step, like any finite element method. So we get a mesh distortion. Then we're going to correct this mesh distortion. So we smooth the mesh. And due to the this mesh movement, we also have to perform a so-called advection step. That means material has to flow through the mesh in order to maintain it, for the material to maintain its original position. Keep in mind, ALE is an explicit method. Yeah, and so we also have the stability limit. Just keep this in mind. And common examples for ALE method are excessive solid deformations, bulk forming, for instance. Some people use it for paste-like materials, glue, for instance. But you also can compute flow-like problems, so tank sloshing, for instance. However, keep in mind, this is not an actual fluid solver. So you do not have any turbulence models. Also, heat transport is not possible at the moment. If ever, I don't know, but for the moment it's not. It's considered as more like a very limited fluid solver, so to say. Yeah, and also try the structured ALE solver, which is an enhanced ALE solver, more convenient for different meshes, mesh refinement. It's usually gives a better performance. Not all the time. I even found cases where it was performing poorer than the original one. And however, one of the drawbacks of the structured ALE is, although it gives better performance most of the time, is less versatile when it considering to geometry and mesh domains I want to analyze. Okay, I think that's it from my side. As usual, if you have questions, later on questions, I'm going to answer question now, but if you have further questions later on, feel free to contact our support. Also check out DYNA examples for a couple of examples regarding the mesh, and DYNA look, the usual resources. With that being said, thank you for your attention, and now if you have questions, write them in the chat. If not, we're going to answer them later on. And there was a question actually. We're not going to share. I'm not sure. I think we're not going to share the link to the YouTube video. But if you go to YouTube, you type DYNAmore Express, you will find it. Yeah, I think give us a few days, and we'll see. There's a question regarding mass scaling, and that's a good question. I think mass scaling is possible, but I'm actually not, to be honest, I'm not sure, and I was never using it. I'm one of these guys who's trying to avoid mass scaling. I mean, I'm mostly doing this multi-physics support stuff, and so I'm not so much into this large simulations where you really efficiently or effectively do a lot with this mass scaling. So I'm really not sure about the mass scaling. I think it's possible also to do mass scaling in ALE, but I'm not sure because I never used it. Okay, there's a question. Which method is better suited to simulate pasty liquids, adhesives, ALE or SPH? Good question. Based on my experience, I had better experience with the ALE method, but I would say none of these is perfect. You can also try to use the ICFD solver with level sets. So basically what you do is you you have your Lagrangian structure, which is somehow deforming the ICFD mesh, and then inside of the ICFD mesh, you're using level sets to compute a distribution of your pasty liquid, so to say. And so far, I had the best experience with this one. So rather than using SPH or ALE, you can go with ICFD. I think I would think about how long is the process. So just keep in mind, SPH and ALE are both explicit methods. So you're constrained with the CFL stability condition. If you have a process which is slow, then I probably would give the ICFD a try. In my opinion, I rather go with ALE than SPH, but I'm not satisfied with both of them for this particular application. Yeah, it's not like these methods are straightforward. I think there's a lot of you have to work sometimes you have to find some workarounds. I'm not satisfied with either of these, to be honest. Okay. Yeah. If there are no more questions, I'm going to stop the session here. Anyway, if you have further questions, just feel free to contact us, and I think we're happy to answer. Okay, just as a follow-up question, last one. I think this applies to ALE and SPH, right? The question is, does it work with all material models? No. The thing is, with ALE, you have all the time this advection step, and advection requires a special treatment also in the material. So a lot of materials are implemented, so the usual suspects, I would say. Give it a try. I mean, LS-DYNA will tell you, hopefully, that this material is not supported. Do a quick example, run a really simple example with your material you want to use in ALE, and then see if LS-DYNA complains or not. Yeah. Okay, there's the last question. Which method is best suitable for internal blast explosions? Simple conweb or ALE? I don't know conweb, so ALE. I really don't know what conweb is. I never heard of this one. And I saw a couple of people, also my colleagues from DYNAmore Swiss, just recently they did an explosion simulation in some mining undersurface facility, some distribution of pressure waves inside of undersurface facility, and I mean was working with LE, and I got good results with this one. So yeah, and there's a comment from my colleague. ALE material models for ALE are stated in the keyword manual. Just check it. Yeah. Okay, so with that being said, okay, last question. Okay, then I'm done. So which boundary conditions are applied on the border of the ALE domain, slip wall or non-slip wall? Okay, because I picked this question because it's actually a really good question, because you can answer the question actually by yourself. Think of what happened in the ALE domain. Yeah, so or what's happened in the ALE method. Yeah, so what we're doing. So first of all, we have the Lagrangian step. Yeah, or maybe let me just go back a little bit. What do we choose? Okay, let's choose, for instance, this one here. Yeah. So the question is, what kind of boundary condition do we have here on the outside? Yeah. Is it a slip, stick? Is it outflow? Is it reflective? What is it? And like I said, think of how the ALE method works. So what we have all the time is first we have a Lagrangian step. That means we're going to apply a load. Yeah. And we have this material. And if let's say I have this structure here, we're going to apply a load here. We're going to push down a little bit of the ALE material. So the first step is always the Lagrangian motion, right? That means we apply down here, we apply a load, we have a deformation here, and then the whole deformation spreads out also to the boundaries, right? So if you now want to have a non-outflow boundary condition, so to say, yeah, what you have to do is, you just have to prevent any nodes moving perpendicular in this direction. That means your boundary condition means the displacement of these nodes in this direction is blocked. If you want to have a no-slip boundary condition here, that means you have to prevent movement of the nodes in this direction. Yeah, and this is how you do it. So think a bit, what do I have to define as boundary conditions for the ALE boundary? Yeah, is am I allowed the nodes to move or not? Yeah. So if I want to have an outflow of material, then I have to keep the nodes moving. I have to prevent any boundary condition here. So keep the nodes moving in any direction as they want. Then if I have an outflow, if I don't want to have an outflow, well, I have to constrain the movement of the material. Yeah, think about it that way. Always have this Lagrangian step and think, if I apply Lagrangian step, the nodes will deform and then correct it back again. Yeah, for you as an out from the outside, it looks like the material is moving inside of the mesh, but it's not true. In the first step, there's always a mesh distortion. And if you prevent mesh distortion or material movement, then this is how you define your boundary conditions. Yeah. Hopefully I answered this question. Exactly. So there's no boundary condition. That means whenever you have an LE domain, material can move out of the LE domain. Yeah. So you have to do something, you have to apply the boundary conditions in order to keep your material inside of your LE domain. Yeah. So for instance, here in this one here, I think it was a nice example. So we have here the bird-like material. I mean, we're lucky because the material doesn't reach the border, but actually here we have an outflow boundary condition. If I want to keep it inside of this one, I have to prescribe, that's a good question now, how I do it in this case. I have to somehow fix the displacement here, and hopefully in this particular case, LS-DYNA moves it with the boundary. There are particular, okay, this is the last one, really, sorry, or this is really the last one. How do you define infinite air domain? There's a keyword called ambient air. I think it's in the boundary conditions. Yeah, so you can define a layer of LE elements on the outside of your domain, and you can prescribe this as an ambient air, and then you can prescribe boundary. This is one way of doing it. But what I suggest is there is in control LE, there's a parameter which is called reference pressure. So this is actually a pressure which you can apply on the outside of your LE domain. And this, I think, corresponds to this is a pressure which you keep constant no matter what the simulation is doing. So this corresponds, I think, to some kind of infinite pressure reservoir, so to say. Yeah. So either you're using the ambient LE boundary ambient, something like this, I'm not sure. Or you can use also maybe give the reference pressure a try. Yeah. Okay, so that's the last question. If you have further questions, feel free to contact us. And yeah, thanks for your attention. And the slides you will find online after I corrected the spelling mistakes. And also the video you'll find on YouTube channel. Just go to YouTube, DYNAmore Express, LE, and you will find it. Yeah, just give me a few days to upload a video. And yeah, and you can rewatch it later on. Okay, with that being said, thank you for your attention, and yeah, see you next time. Yeah, bye-bye.